Let's get started. So this is a shortened session because Luis Paris unfortunately is sick and won't be able to come, which means that we can try to beat the long lines at lunch after the first two talks. So the first talk is a mixed synchronous and asynchronous sessions. Kirstin and Nobuko Yoshida. Kirstin?
Thank you very much. So as Nobuko already told you yesterday, the talk is about distributability. So I hope you are well aware that if you are not concerning distributability, there is no real difference between asynchronous and synchronous communication in terms of expressive power. But if you forbid for anything that reduces the amount of distribution in a system, then synchronous communication is strictly more expressive than asynchronous communication. And the talk is about finding out how we can maybe get a little bit of this additional expressive power to the session type setting, right? So we start with the pi calculus. Here, this is the full pi calculus where you have the choice construct on the very left, and on the right you have the prefixes that can appear in the choice, and you see that there is an input and there is an output, so you can have choices in that inputs and outputs can appear mixed, right? And it turns out for the pi calculus, this is really what makes the difference between the asynchronous communications and the synchronous and the expressive power of the synchronous communication. So there's other things that make a semantics, for instance, asynchronous or synchronous, but the expressive power, the additional that comes with the synchrony, comes from the mixed choice, right? And now I give you one session calculus. You can take the one that you like, but for the sake of this talk, we have this one. And there you can see that we have here selection and branching at the top line, right? And as a form of choice, and it doesn't really matter what kind of choice you find in this binary session types, they are all usually separated choices. So what you have here is you can select exactly one output, or something that resembles the output, because there's somebody taking a decision on what branches to proceed, and then you have on the, so to speak, receiver side several possibilities to react to whatever comes in, right? And so the general idea in that you find of choice that you find in binary session types is that you have some kind of internal choice connected to the sender that makes a decision of sending one of several options, and you have on the receiver hand side an external choice that offers different ways to react to this decision. But that's it. You do not have a mixed choice, usually. Now, and that explains also why I called this calculus CMV. This is because of the three authors, right, of which we have one here. There was this recent addition, this recent extension of this calculus that indeed includes mixed choice. So we have here the choice construct again. I omitted linear and unrestricted prefixes, but they are in the language, but not relevant for this talk, so that's why I omitted them. But you have a choice construct, and then you can use that for the branches, and you see there, you have a label and then a star, and the star is either a bang or a question mark for output and for input. So here you have a session type calculus with mixed choice, right? And that's really nice, and that's really something very new. So you can now express things like that. So you have here several choices in parallel. It doesn't matter that you have two for Y, but you can look at the blue part and the green part to see that for Y we have here a choice between an output and an input, and on the other endpoint of this session, on the X, we have a choice between an output and an input, and that's fine. It's a well-type process in session types. So this is really nice, and it really adds a lot to the flexibility, right? There's examples in the paper for producer-consumers, for instance, where it really makes a difference that you're allowed to do that because you can express a lot of things more naturally. So it's really nice to have that, but and it really increases the flexibility in using this calculus, But then the question is, does it also raise the expressive power? Do you get a bit with this well-typed calculus, with this well-typed terms in this calculus, do you get a bit of the additional expressiveness of synchronous communication, right? And yeah, that's the question that we looked into in a paper that we submitted to, or had at ExpressSOS last year. And what we wrote also there is we do not expect an increase in expressive power for linear choice, but for unrestricted, at least you should expect some increase in the expressive power, right? If you just look at that briefly. Actually, if you ask me, so we wrote that mostly because the reviewers always said, it's obvious that you don't get the expressive power of the full calculus. Nobody claimed it would be, but at least something more. So for me, already for the linear choices, it's not that obvious, right? You have well-typed, mixed linear choices. So is it really not anything more than you had before? It turns out, unfortunately here, the answer is that the mixed sessions do not increase the expressive power. They increase the flexibility quite a lot, and they're really nice, but pure expressiveness, if you consider only the expressiveness when they do not add anything, neither in the linear nor in the unrestricted case. So now what we are doing now is we look at that, try to explain why this is that, like that, so to see what else we could maybe do to indeed get something for the expressive power of synchronous communication, right? So that's the idea. Okay, so how did we prove that it does not increase the expressive power? And believe me, it's really not easy. So I had a first view on this calculus, and of course they asked me some question and I answered that. I had not much time to look at the paper by that time, but I did not spot that it would not increase the expressive power, and this is something I'm really working on much, and I did my PhD on and stuff. And still it really needs a lot of detail and techniques to figure out why you don't get more, right? So it's really not an easy answer or analyze. So why is it that? In the paper, we did the following analyze. So first of all, we took the leader election problem and compared that, because in the pi calculus, to show that there's a difference between the asynchronous pi calculus and the synchronous pi calculus, leader election by Palamidesi was the first what was used to prove that there is this difference, right? So we just revised this proof technique in order to show that there is really also a difference in the expressive power here. But then we went to one of my own research results. We went to the so-called synchronization pattern. It's smaller, it's more wider applicable. It's I show you this, the definition later, but the basic idea of a synchronization pattern is to capture what is what kind of structure you need in a term to have this kind of power in communication, and this starts for synchronous communication. You also have a synchronization pattern for asynchronous communication, and then we looked into whether we find that kind of structures or not, right? So it's more basic. So the idea is basically, if you do not have stars, you cannot solve leader election. But of course, with the stars, you can do more than just leader election. It's not just one problem. So it's not, if you just show that leader election is not possible, there could be something else that you could do with synchronous communication that you cannot do before. So the question is always, do you add something here, right? Okay. And then the third thing that we looked at the paper is an encoding what was given in the original paper, right? And that also tells you a little bit about why you do not really add more expressive power. And now for the talk today, I will talk about these results from this ExpressSOS paper, and then add one more step, which is not in the paper, namely, can we build a semantics, an asynchronous semantics for the CMB plus, for the calculus with mixed choices.
I have a comment that Vasco proved soundness, but they do not prove complete.
The other way around.
We did it.
Yeah, the other way around, but yes. We added the soundless proof for this encoding. Yeah?
So I'm a bit lost. So are there types involved in this diagram? So you have types for byte, types for...
I will come to that, and no. Because the problem with not having the expressive power of mixed choices here is not depending on types. It has nothing to do with the types, the syntax and semantics of the language itself.
And that's the synchronous pi calculus, right? So that's
The PE, it's synchronous pi calculus, yes. So it basically means that you cannot encode into the pi calculus into that because you are missing expressive power in the... I mean, that is not the surprising part, but it's really how much expressive power you miss. That you really don't add something. Yeah.
What do you mean by linear choices?
Linear choices? Did I say? Sorry, if I said...
Linear mix of choices.
Linear, sorry. Linear and unrestricted are the predicates. So, unrestricted is shared names, and linear is the
Session channels.
session channels.
But they are not typed.
I mean, the languages are well typed once, but you don't need the types.
They are typed.
My question is, if you are asynchronous and you have that mixed choice, you break subset reduction.
No,
They have...
This is the synchronous.
It's synchronous. No, if you're asynchronous.
Wait.
Synchronous.
Wait, two things. So the original semantics of the calculus is synchronous.
Okay.
But the expressive power is that of an asynchronous calculus.
Oh,
And that's why we are able to give the semantics using cues.
okay.
That's basically what we do, right?
Yes.
And this last part is the new bit about it. Since the expressive power is that of an asynchronous language, we are able to give the semantics with cues. But you have to do something.
Okay.
You cannot naively do that, because then, of course, you get into all the trouble that you would expect. Deadlocks and additional behavior and whatnot, right?
I'm sorry, I'm very confused. I'm sorry to interrupt. But, so the idea is, so you show that you cannot encode a linear relation in this class language, right? And it's because of the same argument as Palavides' paper.
It's not the same, but it goes along the same lines, yeah?
Yes, and then this enables you to assume that there is something asynchronous about this language.
It's more. No.
It's
It's really
we do
from
not
this...
talk about the last
Yeah,
item.
Yeah.
Let's
I will be
forget
more
the
patient.
last
Yeah.
item. Confused.
We just use that to come to this conclusion.
Okay, so
Okay, so start...
forget about the last item because confused.
Okay, so let's start with leader action. I hope you are all familiar with that.
We are proving synchronous mixed choice has the same expressiveness as without mixed choice,
Yeah.
and we cannot encode usual leader election.
Or anything else that you expect from synchronous.
But let's think only synchronous now because confused.
Okay, so leader election. So what is important here is that it is a symmetric network. If you do not have a symmetric network, you cannot use that to distinguish synchronous and asynchronous communication. So the difference is really, if you have a synchronous network, where synchronous means the processes are allowed to have an ID, but are not allowed to differ in anything except for this ID, and the IDs should not be ordered. So you cannot use the IDs to choose a leader. Every ID has the same probability of being chosen. Right? That's the basic idea. And then you announce a leader by sending an output on the ID. So you use the IDs as channels. That's the easiest way to do that. And then if you are ID free and you want to be the leader and you think you have succeeded, then you send 3. Message on channel 3. Right? That's the way. And then you solve leader election if you have no such 2 messages, and in every run you have exactly 1 of them announcing himself as leader.
And I can only nominate myself because I cannot.
Yeah, I mean, this is the way it works. It's not really required, but for the example, it's basically like that. So this is a leader election in the pi calculus. So this is the terms that you have. You put them all in parallel, right? They're depicted here. So it's a 2 stages. On the one hand side, you have the circle in blue, and you have the communications that are depicted here. For instance, here you have a communication between 4 and 3 on channel C, right? 4 is sending in C output to 3. And the receivers are the ones that winning this binary part. And since we have 5 processes in the beginning, it's exactly 2 communications that are happening. So 2 processes are left for the second stage. And in the second stage, we have the star-like structure, and that then again the receiver of the of the last two processes, right? One is sending, the other one is receiving, and the receiver is still in the game. And you see that that is one of the derivation that you get, and you see in this case number 3 had 1, and there's some junk left over, but that is not observable. So this is just a stuck process that cannot do anything, right? And all the other runs of this term are symmetric to this one. So the only thing that changes is basically you get another piece of junk and you get another leader. But you have exactly one way for each process to win. Or exactly two, I'm not remembering. But it's the same amount, the same probability for every ID. Okay, so this is leader election for the pi calculus. So why does it not work for the mixed session calculus? The problem is we cannot solve leader election in simulating networks of odd degree here, because if we try to do that, we can construct a potentially infinite sequence of steps that always restores the symmetry of the original network. And of course, to elect a leader, I have to do something very asymmetric. Namely, exactly one is saying I'm the leader and all the others don't. And that's not symmetric, right? Symmetry would mean that everybody says I have an output, and the only difference is the ID that is transmitted, but that would not be a solution to the leader election problem. So you can go into infinity and never deciding, or you decide on two different things, or whatever you do, but it's never a leader election solution. And this is the same as with the pi calculus, so the Palamidesi result. The difference now is how we prove that. As in the original case, the main ingredient is a long confluence level, but with the pi calculus, the confluence is about inputs and outputs. In the asynchronous pi calculus, if you do an input, and if you do from the same term an output, then you can do the output here and the input there, and you end in exactly the same state. And this is not true with the mixed sessions. Of course not, you have choices that combine inputs and outputs. So if the input and the output is the same choice, there is no way to do after the input the output, because the choice is gone. So this is not true, so we have to look for something else, but we found something that restores another confluence lemma that gives us the same amount of proving, and this is the following. So you have a starting point with two options, and the one is that from P to P1, the only thing that changes is that there is a choice on endpoint A that is reduced. And in the other case, the only thing that changes from P to P2 is that a choice on endpoint B is reduced, and A and B are not the same. All the other changes for the communication partner happens in Q1 and Q2, and that's not restricted. But for the P1 and the P2, we require that this is really the only change. And if this is the case, then the two choices that are reduced from here to either there or there have to be different choices, because A and B are different session channels. And that means that then afterwards you can close again and reach the confluence. And this confluence lemma was really enough to re-establish the proof that you cannot do the encoding, right? So the reason here, that's why we do that. We look for the reasons. Why was it not possible? So the reason here was because the syntax allowed choices only for a single channel endpoint. That's the point. That's why it still worked, to show that it's not, that you cannot encode the leader election. Okay, synchronization pattern. This is a star. This is the amount. So if you find a process that resembles a star, it means that you have some form of synchronous communication in your calculus. And we basically show, no, that's not the case, you don't find that, and that's way more fundamental. Because this star pattern really represents the minimal amount of what you should see if you have any kind of synchronous communication in the calculus. Why this is the case is another paper, it takes way more time to explain, just bear with me here, or go into the intuition that we derive from that result. But the idea is you have a state, from that you have 5 different possibilities to go on, A, B, C, D, E, and in the picture, you see that there are neighboring steps like A and B, for instance, and they have to be in conflict. So neighboring steps A and B, B and C, C and D, and so on are in conflict. But everything that is not in conflict has to be distributable. So that means completely independent. So if A happens, there's nothing that prevents C from happening later, because A and C are not neighboring. They're completely independent. Okay, again, we find that in the pi calculus, right? That's a star. Easy, I mean, the A action is between these two things, and it's conflict to the B action because it requires this input here, which is removed by doing the step on the A channel, right? But the C channel requires these two choices to reduce the A. These two choices, they are not related, they are distributed. Right? That's the idea. Okay, so why do you not have stars in the mixed sessions then? So this is basically what you have to prove. The proof idea is very simple. If you have a calculus that has stars, you cannot encode it into, via respecting distributability, into a calculus that does not have stars. That's another result that we are really using here, but we do not really have to reprove. And so it suffices to show that there are no stars in the mixed sessions, and therefore assume there is a star with these 5 steps. So that means then in session types and mixed sessions, it means that there are always for every step 2 choices that interact. So every of these steps has 2 choices. And since neighboring choices have to be, neighboring steps have to be in conflict, they have to compete for a choice. And then if you repeat this argument, you really get a structure that needs to look like that, right? You have an A using 2 choices, the B is competing for one of the choices, and another one, it competes with C, and so on and so on. But now the problem is that this is not possible because you need, for one step, you need 2 choices on different session endpoints. So that one is on X, and that one has to be on Y. But for that step to happen, then this one needs to be on X again. For that step, this one has to be on Y. Then for that step, this has to be on X, but then these 2 are on X, so E cannot be a step. Because E cannot reduce 2 choices on channel point X. It needs an X and a Y. And it's not possible to close any cycle of odd degree this way. So you don't find stars. And here the reason is the semantics. You don't find the stars because a channel endpoint can interact only with one other channel endpoint. Right? That's why you don't find them. Okay, so to sum up this part, you cannot solve leader election in symmetric networks of odd degree. You cannot express the pattern star. What you can do, you can express the pattern M. That's the one for the asynchronous communication. That's easily to be found. I did not show that it's in the paper. And from these things, we conclude that there is no synchronous expressive power in this calculus. Right? So it's a corollary, of course. Right? Because there is no formal definition of what is the minimal amount of synchronous communication that you find, but it's really good reasons to say that there is not more. There is even one more thing. There is in the original paper an encoding from the mixed sessions into the calculus without the mixed session, with only a separate choice. And this encoding is good, and it's distributability preserving. So if this calculus had anything more in terms of expressive power, there could not be such an encoding. Right? So it really does not add anything. And we also learn one more thing from this encoding, namely that the difference between inputs and outputs in these choices can be captured by just labels in the encoding. Right? So it's really not more expressive power. Okay, so I promised you that next we would look into a semantics with Q for CMU+, which is not easy. So the named way to do that is, of course, first to add Qs to the system. So Q is just guided Q from one channel endpoint to the other. So we have 2 Qs for each session and one in each direction. And you can add messages, label and the value that is transmitted to the Q. Now what you do is you change the semantics, saying that if you have an output and a Q, then you put the output on the Q and reduce the process. And the matching rule for input then, so you split input and output into rules, right? Is if you have a Q with an output message on top, and you have a matching receiver matching for the label, and of course for the channel, then you can reduce, and by that the Q gets shorter, right? But that's not working, because it introduces deadlocks and new behaviors, right? Very easy. If you just look at these two choices that are combined here, what can happen is that both push their output to the queue, and then what happens is they both reduce to their continuation as 1 and as 3. So either you get new behavior, or the messages on the queue block everything, or there is simply nothing left to do. But it's not what is happening in the original term. Right? So this is not working, so how do you do that? Therefore, we look at the encoding that is given. I told you that there is an encoding in the original paper between mixed sessions and non-mixed sessions. And the idea of this encoding is the following. If you have, again, the term that you have seen in the beginning, the idea is to do the information about input and output into the label. So you can see there's an output blue on the top, and it becomes a label with a question mark here. And the green input becomes a label with an output, with a bang in the encoding. And for the orange output, it becomes an output label. And for the red input, it becomes a red input label. And that's why it works. So there's also some duality in the encoding. And now the question is, where comes the duality from? In the choices, you don't see which of them are external and internal, but the type system still requires them to be internal or external, and that always one internal is combined with an external one. So the type system gives you a type only for this, if you have that. And then from the type, being either external or internal, so the one on the left was the, oh, I forgot. So one is the external, the other one is the internal, and for one you switch inputs to outputs, and for the other one you keep them, and that's why the encoding is working. Okay, so the important part here is not how you deal with the labels, or that this encoding is working. It's not so trivial, you have to look into the paper. But the important point here is that the encoding uses the fact that one of the choices is external and the other one has to be internal. That's the important bit here, and we make use of that by putting this information back into the syntax. Right? We do, again, have two choices. They're both mixed, but one is external mixed, and the other one is internal mixed. And this that we can give a queue semantics, because what you do now is, if you have internal output, then you just do what you are supposed to do, right? You put it on the queue and do the continuation. And the matching input then has to be, of course, external. So you have external input, you read from the queue as expected. But for the other way around, you have to do something clever. And this is, if you have an input, and really you have to start with the external. You always have to start with the external. The external is what's wrong, sorry, with the internal. The internal is always the one that decides. So the plus is the internal, sorry. You have to start with the internal, and if the internal decides he wants to receive, it just does not do the reception because there's no output yet there, right? But it already reduces to this one part and becomes an external choice, and moves the thing, the label, as a message to the queue, just saying, I want to receive. I decided I want to receive next on L. And then, if you have a matching output on an external choice, this can consume this message in order to push the output on the queue. But an external choice is not allowed to push an output to the queue unless it finds this kind of message. And then you can again use this rule afterwards to receive it, and then you're fine. That's the idea. Okay, we did not prove that completely, but we are pretty sure that it is working like that. Maybe you have to do some small adaptations, but yeah, we are pretty sure that it's working like that. So what do we have? It's the last slide. There's an asynchronous semantic for the mixed sessions with queues, which is, by the way, very interesting, because for the asynchronous calculus, what you find is only backs, not queues, explicitly not queues. So for all the session type calculi that we know, even binary, what we find is queues, not backs. So already we do have asynchronous communication, but it's not the same as in the asynchronous calculus. It's a more guided form of asynchronous communication. It's nice, just a side remark. And this is, of course, what we also find here. And we have this result saying that this particular calculus, even though it syntactically has a mixed session, does not increase the expressive power. And what is the important part is, why is this the case? And we see that in this case, it's about syntax and semantics. It's not types. We do not use any types in this proof. It's not the type system that prevents them from reaching more expressive power. But of course, the types are somehow behind that, because they forced, I guess they had the way the syntax and semantics was built in order to make the type checking easy, right? And the main problem was, of course, that you still have external and internal choices. So if you want to add binary session types, really more expressive power, the expressive power of synchronous communication, at least a little bit of that, you would need to somehow divide from that. Because as long as you don't do that, there will always be a way to more or less get the same kind of asynchronous semantics with queues.
Because we can encode it.
Yeah, and so it's not really, you don't reach. So you really have to break with this intuition of having an external and an internal choice. It's not allowed that only one decides. If you have only one who decides what's happened to be next, and not both of them who concurrently decide or something like that, then you don't really get the additional expressive power. And important here, it's not a type system that prevents them, and is, of course, helps us to do that additional bit of expressive power with other calculus. In particular, with maybe this multi-party session type, some things might be easier because you don't have the duality. You don't really need to distinguish into external and internal choices. You don't have duality. From the syntactical point of view and semantical point of view, you don't have the restriction that you have a choice with only one other communication partner. They already calculate that break that, right? So there you maybe reach the additional expressive power more easily.
Okay, I should add one remark. Original Honda Vasconcelos calculus, if we add mixed choice to the shared name, then we can encode, because it has the same expressive power as pi calculus. We can encode this synchronization. The problem is your mixed
The double
session
point.
have two endpoints restricted, so that we cannot represent.
Yeah, the double binder in this case makes
Double binder,
already the
yes.
unrestricted part not having the synchronous power.
Okay, thank you. We'll take some time for questions.
Just a quick question. I mean, am I allowed to say that it's not fully asynchronous? Because in the case where you need to ask, saying I want to do an input and put it in the queue, you are kind of introducing a synchronization there.
Exactly, and it's also the point is that for asynchronous communication you expected output to be non-blocking, and that's not entirely true because it's an internal choice, right? External choice. You have to wait for the decision of the other ones. But then you can push your output before this is received. So the actual sending action is not blocking. It's
So
debatable.
This
but,
is
yeah.
really work in progress. I think we have better encoding if bounded, because Milner has encoding of bounded buffer using synchronous one. And this probably can give more flexibility, but we didn't have time to try that way yet. So we need that. Synchrony and asynchrony. He has argument synchronous mixed choice can represent asynchronous behavior using backward encoding. If we can do this, probably bounded. But probably we can do better, not this kind of one. But we didn't have time to do that. So,
Okay, let's thank the speaker again.